So this problem is asking us about amusement park ride, which is a hollow steel cylinder in which people stand with their backs against the wall. And this cylinder has a 2.5 meter radius. The cylinder starts rotating on about a vertical axis, and eventually the floor goes out from under the people's feet. And due to the centripetal motion, the people will stick to the walls. So the clothing has a static coefficient of friction against steel from 0.6 to 1 and a kinetic coefficient from 0.4 to 0.7. And only people over 30 kilograms are allowed on the ride. The problem is asking us specifically what the minimum angular speed and rotations per minute is for the ride to be safe. So the first thing I did for this problem was just sketch out some drawings to make sense of this. You can see on the right is a free body diagram for what one of the people in this ride, what forces they would be experiencing. Notably, the normal force is perpendicular to the surface, and that normal force is what's going to be accounting for the people's circular motion, while that force of friction opposing mg is what allows people to not slip. So the only way for this ride to work is for the force of static friction to continuously be able to be equivalent to mg. So there's going to be some minimum value for which that's true, and people, or there's going to be some minimum angular speed for which the force of static friction can still overcome that the gravitational force. So the way we can solve for that is firstly, the first thing I did was actually that thing on the right where I went ahead and solved for normal force. Since I knew that normal force is what's going to account for this circular motion in this, I set that equal to mv squared over r, the centripetal force. And you get, we know from these units that centripetal acceleration is equivalent to v squared over r and angular speed squared times r. And since the problem was asking for angular speed, I went ahead and substituted that in instead, giving us that normal force equals mass times angular speed squared times r. And then on the right, you can kind of see why the main reason why we know that we can equal n to mv squared over r, just the fact that vertically the system has to be in equilibrium, meaning that the force of static friction and mg are going to have to be equivalent. So that gives us that the force of static friction equals mg, but that isn't quite enough to solve for that minimum angular speed, because we also need to account for that coefficient of static friction, which the tricky part is kind of figuring out whether we should use the biggest coefficient of static friction or the smaller one. In this case, it's going to have to be the smaller one because we want to make sure everyone's safe. So it's the 0.6 that's going to be the most necessary. And we can account for that by acknowledging the fact that the coefficient of static friction times normal force is also equivalent to static friction, and we already found the normal force, and we can just plug in that normal force and make it equivalent to that earlier force of static friction, mg. And once you do that, the masses will cancel, giving us that angular speed is going to be the square root of gravity over that coefficient times r. And we already discussed that that coefficient is going to have to be the 0.6, that static one, since the person is, we don't want them to move. You only use the kinetic coefficient when there's actual motion that's being opposed. And we get that omega equals 2.56 radians per second, and we can't forget to convert that to rotations per minute, and once we do that, we get 24 rotations per minute for the answer to this problem. So that's it. Thank you for listening.